Hello, my name is Robert Xing, and my partner is Sirui Wang, and we will be presenting our research project, Lossy Compression for Convolutional Neural Networks. Convolutional neural networks, CNN for short, is a deep learning technique that excels in solving computer vision challenges. More specifically, they are some of the best solutions to object detection and image recognition today. Convolutional neural networks can achieve this by transforming an input through a convolutional layer, a pooling layer, and then a fully connected layer. These layers can be repeated multiple times to develop the network. The number of neurons created by these layers can be outstanding, and operations done for each progressive layer can be extremely computationally demanding. However, most of the time it takes to train a CNN happens during the convolutional layers. Like most deep learning techniques today, CNNs are typically trained on an accelerator like the GPU. The high throughput and parallelization of the GPU is a necessity to complete training in an acceptable amount of time. According to a review of deep learning by Schmidt-Midhuber in 2014, GPUs can train convolutional neural networks several magnitudes faster than a CPU can. However, even on a GPU, CNN models can take hours to days to train, partially because of the large input and parameter size. Presently, the Large-Scale Visual Recognition Challenge, ILSVRC for short, uses ImageNet, a database of 15 million annotated images, to push research in computer vision technology. The leading object detection method in 2017 with the highest precision also uses a CNN. And also, the leading image classification method with the lowest error in 2017 utilizes a CNN with over 27 million parameters and 1.28 million training images. This leads us to our research question. How can we implement effective compression on the parameters and input of a CNN to reduce the time it takes to train and test the data? Now, some of the challenges we face to compress the input and parameter for CNN are experimenting with different methods of compression to ensure that a CNN can maintain a high accuracy and precision despite applying lossy compression. Another problem is how can we minimize the overhead of compression so that we can actually achieve an overall performance improvement? Finally, and this ties to the second issue we discussed, what method of compression can be decompressed parallelly by the GPU? Here is some background to using compression to decrease the size of CNN parameters, and therefore increase the speed of training and testing. Song Han et al. In 2015 were able to compress deep neural networks through quantization and weight sharing without losing accuracy. More on these methods later. J. Wu et al. In 2015 were able to use quantization of convolutional neural networks to produce speed-up and compression while losing minimal accuracy.
For the motivation of our project, we know that neural networks are both computationally intensive and memory intensive. That will make them very difficult to deploy on embedded systems with limited hardware resources. The large number of weights of the neural networks consumes considerable storage and memory bandwidth. For example, the AlexNet CAF model is over 200 MB, and the VJJ16 CAF model is over 500 MB. Neural networks are mainly focusing on visual recognition nowadays, which will take images as their input. One high-resolution image can be up to 10 MB, and the training set can contain up to thousands of them. That will cost a lot of memory and bandwidth. Also, the peak bandwidth between the device memory and the GPU is much higher than the peak bandwidth between the host memory and device memory. This disparity means that the implementation of data transfers between the host and GPU devices can make or break the overall application performance. We can look at one real-world example. The architecture given by Chris Whisky accepts images of size 227 × 227 × 3. On the first convolutional layer, it uses neurons with receptive field size 11, stride equal to 4, and no zero padding. So we can do calculation using one dimension of the image 227 minus the receptive field size 11, and then divided by the stride 4 plus 1, we'll get 55. And since the convolutional layer had a depth of 96, the convolutional layer output volume will have the size of 55 times 55 times 6 times 96. So this will get 290,400 neurons in the first convolutional layer. And each neuron will have 663 weights and 1 bias. So multiplying them together, we will have more than 100 million parameters for the first layer of the conv net alone. So that's a lot of parameters for only a single layer. Then we can look at this graph. This is the relationship between the transfer time and the megabytes per transfer. You can see that no matter it's non-pined or pined to or from device at around 8 kilobytes, the transfer time always starts to increase linearly at a slope around 0.1. Therefore, we can tell that if we compress the data, we can have a significant improvement on the transferring time. We can also tell that by compressing the parameters, we can achieve high compression rate with no loss of accuracy. And if we do compression on images, the accuracy might reduce slightly, but we can still conduct experiments to look at the trade-off between them. Current status of our project, we found a good compression method based on Song Han's paper. Deep compression, compressing deep neural networks with pruning, train quantization, and Huffman coding. From this paper, we're mainly focusing on quantization and weight sharing. This method can help us limit the number of effective weights we need to store by having multiple connections sharing the same weight, and then fine-tune those shared weights. We can look at an example from the right figure. We're supposed to have a layer that has 4 input neurons and 4 output neurons. Then the weight is a 4 times 4 matrix. On the top left is the 4 times 4 weight matrix, which are the parameters, and on the bottom left is the 4 times 4 gradient matrix. The weights are therefore quantized to 4 bins, denoted with 4 different colors. This is done by doing k-means clustering. All the weights in the same bin share the same value. Thus, for each weight, we then need to store only a small index into a table of shared weights and the shared weights themselves. During update, all the gradients are grouped by the color and summed together, multiplied by the learning rate, and subtracted from the shared centroids from last iteration. Therefore, we can get the fine-tuned centroids. We can calculate the compression rate to be 3.2. How? From the above, we can see that 16 times C2 is the original size. 16 means there are 16 weights. C2 is the size of the sign float. Then we look at the bottom. 4 times 32 comes from there are 4 centroids, and each of them will take C2 bits. And 2 times 16 means because we are having 4 clusters, we then only need 2 bits to identify each of them. And there will be 16 nodes. So therefore, we can result in a compression rate 3.2. Also, when we look at images, we can see that they are also represented as metrics. So we think the same method can be used with small shared weights. For our future work, we will first implement the compression method to ordinary metrics for simple calculation and find inspiration towards neural network application. Then we will implement the method to neural network parameters and input images. After that, we will look at the trade-off between the compression rate and the accuracy of the neural network. Finally, we want to implement the method into multi-GPU architecture and get better performance. I think our project is of great importance, because our work can really make neural network less heavy and therefore be able to apply on mobile systems and other systems with limited resources. More basically, we can just accelerate the processing speed of the neural network. If our project goes well, we can even come up with better GPU-based solutions for neural network applications. That's all. Thank you.